conservative force is a force with the property that the work done in moving a particle between 2 points is independent of the taken path. Equivalently, if a particle travels in a closed loop, the net work done by a conservative force is zero. A conservative force is dependent only on the position of the object. If a force is conservative, it is possible to assign a numerical value for the potential at any point. When an object moves from one location to another, the force changes the potential energy of the object by an amount that does not depend on the path taken. If the force is not conservative, then defining a scalar potential is not possible, because taking different paths would lead to conflicting potential differences between the start and end points. Gravity is an example of a conservative force, while friction is an example of a non-conservative force. In formal definition, informally, a conservative force can be thought of as a force that conserves mechanical energy. Suppose a particle starts at point A, and there is a force F acting on it. Then the particle is moved around by other forces, and eventually ends up at A again. Though the particle may still be moving, at that instant when it passes point A again, it has traveled a closed path. If the net work done by F at this point is zero, then F passes the closed path test. Any force that passes the closed path test for all possible closed paths is classified as a conservative force. The gravitational force, spring force, magnetic force and electric force are examples of conservative forces, while friction and air drag are classical examples of non-conservative forces. For non-conservative forces, the mechanical energy that is lost has to go somewhere else, by conservation of energy. Usually the energy is turned into heat, for example the heat generated by friction. In addition to heat, friction also often produces some sound energy. The water drag on a moving boat converts the boat's mechanical energy into not only heat and sound energy, but also wave energy at the edges of its wake. These and other energy losses are irreversible because of the second law of thermodynamics. Path independence. A direct consequence of the closed path test is that the work done by a conservative force on a particle moving between any 2 points does not depend on the path taken by the particle. This is illustrated in the figure to the right. The work done by the gravitational force on an object depends only on its change in height because the gravitational force is conservative. The work done by a conservative force is equal to the negative of change in potential energy during that process. For a proof, imagine two paths 1 and 2, both going from point A to point B. The variation of energy for the particle, taking path 1 from A to B and then path 2 backwards from B to A, is zero. Thus, the work is the same in path 1 and 2, that is, the work is independent of the path followed, as long as it goes from A to B. For example, if a child slides down a frictionless slide, the work done by the gravitational force on the child from the top of the slide to the bottom will be the same no matter what the shape of the slide. It can be straight or it can be a spiral. The amount of work done only depends on the vertical displacement of the child. Mathematical description. A force field F, defined everywhere in space, is called a conservative force or conservative vector field if it meets any of these three equivalent conditions. 1. The curl of F is the zero vector. 2. There is zero net work done by the force when moving a particle through a trajectory that starts and ends in the same place. 3. The force can be written as the negative gradient of a potential. The term conservative force comes from the fact that when a conservative force exists, it conserves mechanical energy. The most familiar conservative forces are gravity, the electric force, and spring force. Many forces are not force fields. In these cases, the above three conditions are not mathematically equivalent. For example, the magnetic force satisfies condition 2, but does not satisfy condition 3, and condition 1 is not even defined. Accordingly, some authors classify the magnetic force as conservative, while others do not. The magnetic force is an unusual case. Most velocity-dependent forces, such as friction, do not satisfy any of the three conditions, and therefore are unambiguously non-conservative. Non-conservative forces can arise in classical physics due to neglected degrees of freedom or from time-dependent potentials. For instance, Friction may be treated without resorting to the use of non-conservative forces by considering the motion of individual molecules. However, that means every molecule's motion must be considered rather than handling it through statistical methods. For macroscopic systems, the non-conservative approximation is far easier to deal with than millions of degrees of freedom. Examples of non-conservative forces are friction and non-elastic material stress. However, general relativity is non-conservative, as seen in the anomalous precession of Mercury's orbit. However, general relativity can be shown to conserve a stress-energy momentum pseudotensor. References